Hi, folks, and thanks for joining us for our NED Talks this year. We're very proud to be able to not only be doing these NED Talks for NOAA, but also for World Space Week, which is this week. Having said that, we do have a short statement that we want to make.
Sure. In the wake of Hurricane Helene, we want to acknowledge the severe impact it has had on the Asheville community, including our NOAA colleagues.
Many of NOAA's data services from the National Centers for Environmental Information are currently unavailable as we work to restore them. NOAA's weather.gov and our weather forecasting products are not affected by this partial outage. So we greatly appreciate your understanding and during this time, and send our heartfelt support to all those dealing with the aftermath of the hurricane. With that, Juan Pablo, please, will you introduce yourself?
Sure, thank you. Hello, everybody. My name is Juan Pablo Hurtado Padilla. I am the visualization lead for the Science and Industry program that we have back here, and I'm here with my colleague.
Hi, folks. I'm Rafael de Ameller, Rafa. I am the lead for the NOAA Environmental Visualization Lab. I live nearby in Bethesda. We're here in Silver Spring today, and I'm originally from Spain. And, I wanted to mention that we're going to ask folks to please give their names in the Q&A box. You'll see that underneath us, there's a Q&A box where you can enter your questions, but you can also let us know things like your name, where you're calling from, and we'll use that information and, just give you a shout out if you want.
Yeah, we're going to have a couple of questions for you, so please use that box to send us your answers.
Yeah, and we also have in the behind the curtains, if you may, Amanda Keener, one of our NOAA VisLab colleagues. She's taking care of all these questions coming in and everything. So thanks, Amanda, for helping us out.
All right, while we wait for your responses and let us know your name and where you're connecting from, let's start this program, Rafa. So what are we going to be talking about today?
So yeah, we're talking about climates, right? We're all familiar with the Earth's climate. It's the climate we live in every day. But, did you know that other planets have climates too, right? Now, there's a first question that we need to put out here, right? Like, what is climate?
I think that's a great question, yes. We're going to be talking all about climates today, so I think we have to have a definition. And I might say that this is the great opportunity for us to start asking you questions. So if you have an idea or a definition of climate, share with us, and we're going to read it live here. So Rafa, what do you think about climate? Let's think about that word a little bit.
Yeah. So, when we think about things like weather and climate, right? Weather is what you feel at every moment, right? Like how hot or how cold it might be if it's raining. But when you look at weather over time, right, there's a pattern. Have you seen that there's a pattern with weather?
Absolutely, yes. I think, for example, if you are in winter in Washington, D.C., it might get a little bit cold. So you have to prepare your jacket and things like that. So I guess that's something that happens every year. So we have a good record of that, right?
Yeah, we might not know exactly the temperature on a cold day in January here in Washington, D.C., but we do know it's going to be cold, right? That small variability that happens day to day, that's our weather. But the long-term trends of what weather does is climate.
Awesome. And I guess we have a couple of people that are already sending us their names and where they're connecting from. So let's give a couple of shout outs. So we have Amber from Dublin.
Wow. Hi. Thanks for joining.
Yeah. We also have Bruce Glover from Boston and Lynn from Silver Spring.
Right here. Yeah.
All right. So thank you all for joining us.
Thanks, folks.
And remember, please send us your ideas about what's climate for you.
So, we're going to start talking about other planets now, right?
Let's do that.
And, the reason why we are interested in talking and looking at other planets is because other planetary systems help us understand our own Earth systems, right? So we have, if you may, several experiments in the solar system of climate that we can look at and understand a little bit better our own very experiment here on Earth.
Absolutely. And I bet many of us are going to feel very, very lucky to be on this planet.
I'm sure. We also want to give a big thanks and shout out to NASA for our NOAA's sister agency. Here at NOAA, the National Oceanic and Atmospheric Administration, we monitor the Earth continuously 24/7 to understand how it looks now how it's looked in the past and how it will look in the future, right, with our forecasts. Now, for other planets, like the planets we have lined up here, we are going to use a lot of NASA imagery from a lot of missions that they've put out there into space to look at these different planets. So thanks, NASA.
All right, so let's start with the first one. So we're gonna put up Mercury up here. So Rafa, Mercury, the planet is closer to the sun. Just because of that, I think it might be a really, really hot place if you are facing the sun. Is that right?
It can get pretty hot on Mercury for sure, right? So what we're showing up here is some enhanced imagery. You can see some colors in it, but it's so that our eyes can see it better. Because, really, if you look at Mercury, like what do you see here on Mercury? What does it remind you of?
It actually reminds me of the moon. There is so many craters, and you can see like a bare surface. There is not a lot of features there other than craters.
That's right. It's a heavily cratered surface like our moon. And, there's no weather to wear down the craters. So you see very old, ancient craters on the surface. And, there's no atmosphere. You can see that because of that lack of atmosphere, there's no erosion happening, right? We don't see anything like that. So it's very similar to the moon in that sense. But what's different is that there's a lot of dark compounds on the surface of Mercury that make it very dark. What exactly is making it dark? Could be ferrous oxides or oxides or carbon. That's still a little bit unknown. But it's not as bright as the moon. It's darker than the moon, and that's why we have to enhance it a little bit so that we can see it here.
Very good, very nice. So we can say that we can expect Mercury to look like that because it doesn't have an atmosphere.
Exactly. And as you were mentioning from the beginning, we have these extremes, right? When Mercury is orbiting the sun, the part that's facing the sun is going to get boiling hot, super hot on the surface. Again, no atmosphere, so there's no real heating of any air. But that the surface becomes so hot actually that it's some of the different atoms and molecules start ionizing and coming off of the surface. Wow. And when you look at Mercury through certain lenses, like a sodium lens in the telescope, you can see a tail coming out of it, like a comet of stuff that's being blasted off from the Mercury surface by the sun. But then as Mercury rotates and that same side is now facing away from the sun, it almost immediately gets into very freezing temperatures, extremely low temperatures on the other side, right? Because again, there's no atmosphere, there's not that interesting combination of how much time Mercury's different surfaces are facing towards the sun, right? But we do know that there's very little tilt. So, Mercury, the north and south poles don't really see any seasonability.
Yeah. Okay, well, that was a very interesting and rocky planet. So let's move on to the next one.
Yeah.
So what do we have next?
Well, right after Mercury, the next planet that we have come up, what if I told you, Juan Pablo, that there's this planet that's very similar to the Earth in composition, in size, the closest planet to the Earth as far as orbit from the sun? Would you expect it to look a lot like the Earth?
That's a very good question. I'm not sure. Why don't you tell me more about this?
Well, it's pretty obvious, right, that Venus, this sister planet of the Earth, which is very similar in size and composition, and it has valleys and volcanoes and mountaintops and ridges. But when we look at it from outer space, we just see this very hazy and cloudy picture, right? So what's happening here is that even though Venus is very similar to the Earth in size and composition, its atmosphere is drastically different. Most of Venus' atmosphere is carbon dioxide, which we know is one of the greenhouse gases that planets use to keep themselves warm. But in this case, it's a very, very high concentration of CO2, of carbon dioxide. And all that carbon dioxide is creating what's called a a greenhouse, like a major greenhouse.
A runaway effect.
A runaway
Wow, yeah.
greenhouse effect.
Okay.
Thank you.
So, and something that I noticed, for example, in this image, is that we are looking, maybe people don't recognize this as Venus because they might be more used to this image of Venus that we have down here, which is actually just the surface.
That's a really
But we were looking at how actually it looks from space with all those clouds, that very thick atmosphere that it has.
Yeah, that's a really good point. Thank you, Juan Pablo. Yeah, we were fortunate enough to be able to send missions to Venus to look at its surface. And in the 90s, we had a mission that had a radar, an active radar pinging the surface and measuring that surface of Venus through those very dense clouds so that we can get this really good picture of the whole Venusian surface and understand a little bit better what those surface dynamics are, right? Like one thing that we've observed in Venus is that there's no plate tectonics like there is on Earth.
Mm-hmm.
So that's a major difference, right? On Earth, plate tectonics drive subduction and it drives chains of volcanoes. The crust is opening and coming together. Continents are splitting apart continuously, right? Over this warm mantle. Now, there is warmth within Venus, but those dynamics, that convection that happens in Earth's mantle is not happening on Venus. So what we have on Venus is, yes, big surfaces with big volcanoes. Probably some resurfacing is happening because the surface is relatively young because of those volcanoes, but it's not happening along plate lines like it does on Earth. Now, that might also have repercussions on other systems on Venus.
For example, let's go back to Mercury a little bit. We saw that Mercury didn't have an atmosphere, basically at all. Venus is the complete opposite. So we remember in Mercury, you could be just scorching under the sun and freezing if you are not facing the sun. What will be the situation in Venus, for example, with all that thick atmosphere?
Yeah, well, it's interesting because if you're on the surface of Venus and you can survive long enough because of that really thick atmosphere, it's like crushing pressure on top of you and tremendously high temperatures that are melting lead. Venus' surface actually reaches temperatures that are higher than those high temperatures on Mercury. So this greenhouse effect, right, is not just taking, and Venus is further away from Mercury. You would expect, well, shouldn't it be hotter on the surface of Mercury because it's closer to the sun?
Yeah.
And normally that's the case, but because of this atmosphere that Venus has, we end up having a very high temperature across all of the planets.
Very nice. And we also have a very interesting comment from Bruce in Boston that says that it rains battery acid in Venus. Is that right?
So it's true that Venus, those clouds that we were looking at before, there's high clouds that are made of sulfuric acid. And what's interesting is that those clouds, as they precipitate, as it rains, because near the surface of Venus, the temperatures and the densities and the pressure is so high, that rain never makes it to the surface. It kind of like evaporates and turns into its molecules and runs back up into the high levels of the atmosphere where those clouds are, and turns back into sulfuric acid again and again.
Okay, well, I guess my car is gonna have to be refilled for the battery acid in a different place.
That's right.
Okay, let's move on now. What is our next planet, Rafael? Let's put it on the sphere.
So let's see. As we move on, now the next planet would be Earth in order.
It should be.
Right? It should be Earth if we were going in order. But folks, for now, if that's okay with you,
Absolutely.
we're going to skip the Earth because we want to come back to the Earth later.
We're going to save best for last.
We're going to save the best for last. That's right.
Okay.
So we're going to go to Mars now. And Mars is pretty incredible because Mars, even though it has a very, very thin atmosphere, right? You can you don't see really any clouds over Mars normally. There are times when you have dust storms happening in this very thin atmosphere. It's about 1% of Earth's atmosphere, right? So, we can't really breathe on it without a breathing device. But it is enough to create a climate.
That's very interesting.
Yeah. And this climate, you can notice in times on the equator, you have 70 degrees Fahrenheit, 20 degrees Celsius, which is a very pleasant temperature. But that's the best you're going to get on Mars. That's the best, like on the equator when the sun is the highest.
But that's very interesting how we can see the differences between the planets, right? In Mercury, again, we have this scorching sun and completely freezing nights. In Venus, we have, due to the atmosphere so thick, we have a very homogeneous, incredibly high temperature all over the planet. Then Mars, which has some atmosphere, not as good as ours or as thick as Venus, still has this some variability in temperatures due to the atmosphere, right?
Yes. And, you know, as far as we know in the solar system, Mars has the most similar climate to Earth, right? Which makes us believe that we might be able to go to Mars.
And I remember when I was playing with the sphere, I brought down the poles here, and I saw something very interesting there. What is that, Rafa?
Yeah, so Mars has polar caps. And they're made up of icy water mostly, and seasonally there's dry ice, frozen carbon dioxide that deposits on top of that frozen ice that's in the poles. The North Pole is a little bit larger than the South Pole, but what's most interesting is that they're very dynamic. They change depending on what season. Seasons.
Oh,
Mars has seasons.
So I think it's the first planet that we have been talking about that has the word seasons.
That has the word seasons.
Okay,
yeah,
very nice, right. Very nice. Okay, so
and, you know, one other thing that I would like to mention about Mars is that right now you can't find liquid water on its surface. So that water that I mentioned that was in the poles, it's frozen in the poles, but as soon as it gets warm enough, it's gonna turn into gas, right? You're hardly gonna see any liquid water on the surface of Mars because of the low pressure and the temperatures. But having said that, when we look at Mars, thanks to all these different rover explorations that we've been doing, we have found evidence of rivers and possibly an ocean having been there in the past, because we can see deposits that are typical of running water on the surface like we have here on Earth. But of course, we know that there's no running water anymore on Mars. So this tells us that at one point in Mars's history, there was free water on the surface. And when we look at Mars right now, right, to understand, well, how can it have running water? It must have had a much denser atmosphere. So where did that atmosphere go? What do you think happened with its atmosphere?
That's a very good question. I remember when I studied the Earth that one of the ways that we are protected and our atmosphere is protected is because we have a magnetosphere.
That's right.
That's protecting us from all the things that are coming from the sun, right? So maybe Mars had a magnetosphere, but maybe it went silent.
That's exactly right. So as Mars formed, like the other rocky planets in the solar system, what happened is because of gravitational forces, you had a lot of energy forming inside of them, and some other things like the decay of radioactive materials brings this internal heat to the planets. But most of it comes from this primordial formation, right? Over time, planets have been cooling down. The Earth has been cooling down. Venus has been cooling down. All planets, after they're formed, start cooling down, right? Because Mars is smaller, we believe that its interior has cooled down a little bit faster than Earth's, right? So what might have been an active dynamo-type magnetosphere, which is what Earth has because of its core, Earth's interior, we have a solid core rotating inside of a molten core. And the core is made up of iron and nickel, right? This dynamic on the Earth creates a dynamo that creates a magnetic field that extends way beyond Earth's surface, right? And protects us, as you said, and it protects us. Mars lost that protection millions of years ago. So what's happened is that over time, as it was losing that magnetic field, at the time we're assuming it did have an atmosphere with water on its surface, but little by little, as that magnetic field dissipated, the sun's solar energy, the energy coming from the sun, the solar wind, started chipping away at that atmosphere, blowing off into space those different components, like water components, and basically drying out Mars and leaving it with a very, very thin atmosphere.
Very nice. Every time that we keep talking about these topics and we go through planets, I feel even more and more lucky to be on our planet.
You should.
And we have a very nice comment from Rob that was asking, does Mars have sandstorms like in the movie The Martian? Have you seen that movie, Rafa?
I have seen that movie. One of my favorites, I gotta say. I like a lot of science science fiction stuff.
So those sandstorms actually happen in Mars.
Those
right?
sandstorms happen in Mars, and they're quite incredible because in the short periods, like over what we believe is weeks, the whole planet can end up covered in the sandstorm. So all these features that you see, like this volcano here, which is the biggest volcano in the solar system, by the way, right there. And all these other volcanoes and all the incredible chasms and all these features get completely covered by sand. And it just becomes like a big orangey red dot.
All right, very good. Now it is time to move on, fly a little bit far away from our sun. However, first, we have seen already 3 very interesting planets, and I think they all have something in common, right, Rafa? What if we ask our audience if they can tell us what that is?
Yeah. So folks, can you tell us what, from these planets that we've seen so far and what you know of the Earth, right, and what we've discussed here, what do you feel is the commonality between Mercury, Venus, Earth, and Mars? What makes them, what characteristics are similar in all of them? Any thoughts on that?
That's very interesting. Well, something that I noticed is that first, they are not huge planets. They are right-sized planets, and they all have like a solid surface on them, right? Not all of them have atmosphere, so that's not something common between them, but definitely seem like they have something solid there where you can plant your feet, if you could, of course.
Yeah, that's right. So, these are the rocky planets. They're, I don't know, folks are starting to give in some comments there. The rocky planets, right, all share this similar composition where they have a dense core in the middle, and thank you, Juan Pablo, for
put it up there,
right?
Yeah.
So and we have Bob here manning the camera from the NOAA studio. Hey, Bob, thanks. Bob, could you zoom in here a little bit, please, so that we can see a little bit closer? And what you'll see here is, starting all the way over here with Mercury, right, is the first planet we talked about, and you can see that inside it has a very large iron and nickel core. It's the biggest one that we've seen so far, the solid one. We also believe that Mercury might have some molten activity going on inside, maybe because of the tidal forces. Being so close to the sun, right, creates a lot of gravitational energy inside of the planet. Next here in line, we have Venus, which we talked about. And Venus and Earth actually side by side, if you look at them, they're very, very similar, right? We know more about the Earth and kind of like where those layers end, and Venus, we're not exactly sure like where a molten core might start and stuff like that. But as I mentioned before, the main difference between Venus and Earth's interior is how that energy is being moved around and that heat inside, right? And you can see here a tiny little moon, which we also put in there, because the moon also shares all the characteristics of these rocky bodies, right? So much so that it looks very similar to Mercury.
Yeah, it does.
And finally here we have Mars, which, as you can see, size-wise is smaller than Earth and Venus. So it kind of like stands to reason that as it cooled down, it would have cooled down faster because it's smaller and no other big events happened to it along its history.
And we have a very nice question from Hendrik. And probably we're going to leave it by the end, but it's a very good question to keep in mind. Given what you say about Mars' core, do any activity in Earth's core affect our climate? I think that's a great question, and we're going to talk about it a little bit later. So thank you for that. Okay, so we went over the rocky planets, so let's move on towards a different kind of planets, right?
Yeah.
What do we have here, Rafa?
So here, what we're going to bring up is the first of the gas giants, and this is in order after Mars. We do have Jupiter, and Jupiter. It's I I mean, when you look at it, it's just mesmerizing, right? I could look at it for hours. It really is. It's a tapestry of clouds, right? Colorful stripes, bands going in different directions. What do you think is happening in these bands?
Well, the first thing that I think when I see this is clouds. And when I think clouds, there's definitely an atmosphere. Now, probably you can talk more about the atmosphere, but it's very interesting to see all those things. And I have to say that the red eye definitely reminds me like a huge storm, like a hurricane even.
That's right. So, it's very interesting because each one of these bands are like convective bands, and they're moving all that energy that's inside of Jupiter out to the surface. Now, here's what's interesting too. Jupiter is so far away from the sun that the amount of energy that it naturally emits is higher than the amount of energy that it receives from the sun. So these atmospheric dynamics that we're seeing here are driven by both the sun and the interior heat. Of course, the sun still is the most important energy supplier to atmospheres in the whole solar system. But in this case, for the giant planets and like Jupiter, what's happening is because it's so massive, there's a lot of gravitational forces inside that are creating a lot of heat. So everything inside of it, which is mostly hydrogen and helium, like the vast majority of elements inside of this giant planet is hydrogen and helium. And then it has some other components like ammonia and water. That's why you can see differences in the clouds, right, at the higher levels. But as soon as you dig in a little bit deeper, you go from clouds to this really thick hydrogen atmosphere that gets thicker and thicker and turns into a liquid. It turns into a giant hydrogen ocean that, as you get even deeper and deeper towards the core of the planet, it becomes metallic hydrogen.
Wow.
Yeah, so that's the intensity of the gravity pulling everything together has transformed the state in which these atoms normally find themselves into this hyper state.
That's very interesting. So now we mentioned that even though they are gas giants, they might have like a solid core after all, or almost solid.
Yeah.
So will that create a geomagnetic field around the planet?
Yeah, so the core itself in the center of the planet, we're not really sure if there's like a rocky interior or maybe like boulders of other things that Jupiter might have absorbed, like comets, right, or other planets. But outside of that center core, which we're not really sure what it might be, there is a big metallic hydrogen area, which is very conductive. And it's doing, again, this effect where you have a magnetic field outside of Jupiter, thanks to this hydrogen metallic area within the planet.
That's very, very nice.
Yeah.
Okay, so this is our first giant. Let's go to the second one.
Yeah. So, after Jupiter, our next and arguably most beautiful planet is Saturn. Now, when we look at it here, we can see the sphere, but we're missing something here, right?
Yeah, we can.
Let's do. Okay. So
make
we're gonna be the rings, Saturn's rings here for a minute, so that you'll understand that outside of Saturn, there's this very beautiful rings that other planets have, but none are as shiny and as brilliant as the ones on Saturn.
Let me put it there.
Oh, excellent. Thank you so much. Yeah, there you can see the rings sticking out there at the top, right? And yeah, that's a beautiful perspective looking at like from the North Pole of Saturn. And there's another really interesting thing that you might notice here. And this is not a typo. This is not a mistake in the image.
This is not Photoshop.
It's not Photoshopped, exactly, right? There actually is a hexagonal sized feature in Saturn's atmosphere. Yeah, if you could zoom in there a little bit, Bob.
Let's look it up.
Yeah, let's tilt. We're going to actually tilt the planet so that you can zoom into it. Yeah, because we have the whole planet here, right?
Yeah.
So why not zoom into it a little bit more? So that's happening because of fluid dynamics all around the planet, right? And it's the same story as we've observed in Jupiter, where we have these bands of clouds and these atmospheric bands going around in different directions. they're all doing their basically trying to get all the heat to become homogeneous across all the planet, right? So that these are convective cells, just like we have on Earth's atmosphere, convective cells that are basically bringing the hot air up and bringing the cold air down, right, continuously. The same thing happens in these planets here, and that's why we see those bands and cells at different latitudes along the equator.
However, there is something different between Jupiter and Saturn. Saturn is a little bit smaller, so it might have a little bit less of gravity. So how will that affect the atmosphere there, for example?
That's a really good point, yeah. So what we're seeing is because Saturn is not as massive as Jupiter and its density is lower, actually Saturn, if there were a lake big enough to put Saturn in, it would float. Yeah, its density is actually lower than the density of water, so it would float on water. That's because of all that hydrogen inside of it, right, and light compounds in it. But even despite this, it's a very similar composition as Jupiter's, and as you mentioned, because it has less gravity, it's not pulling in the atmosphere as much, so you end up with like a more haze coming out, like a bigger cloud deck, if you may, right? So it's the clouds and the haze are covering up more of the features of Saturn, so you can't see the turbulence as clearly as we can see it in Jupiter. But I promise you, it's happening, because as soon as you go in, the same thing in Saturn as you see in Jupiter happens. That cloud level turns into mostly hydrogen and helium atmosphere that at depth turns into liquid, and then even deeper into metallic hydrogen, right? And same processes as we see in Jupiter, we see them in Saturn.
Very good. So for example, if we talk about a possible metallic core in Jupiter, it will be the same in Saturn?
That's exactly right.
Thus, it will have a geomagnetic field around it.
And it has a magnetic field.
Okay.
It's generating a magnetic field because of those dynamics within the planet.
And you know what happens when the sun interacts with that kind of field, right?
I think we all do,
So
right?
let's put on the sphere, actually.
Yeah. Auroras. So Saturn and the other gas giants, actually, they have auroras. So what is an aurora? Do you know what an aurora is?
Well, I think, and you can correct me, when the particles interact with the geomagnetic field, they get channeled to the poles because of the shape. They interact with the gases on the atmosphere, and they become fluorescent because of the change of energy.
Yeah,
right?
Yeah, it's the sun's energy, right? The solar wind interacting with these magnetic fields. Wherever the magnetic field dives into the planet at the poles, right? The particles from the sun have a chance to kind of like find their way in and excite all the ions and the particles in the upper atmospheres, creating these auroral effects. So we see it in Saturn, we see it in Jupiter too, and we've seen it in the other gas giants.
And just in case, folks, we just had a couple of big explosions in the sun, so we might be able to see a couple of auroras down here on our planet. So if you live far up north, you're a lucky person.
Yeah, of course, auroras, the intensity of the aurora is dependent on the activity on the sun,
Yes.
right? And the sun, the energy output from the sun is very constant, but at different times, features on the surface of the sun where magnetic fields are buckling or breaking, you'll see flares or coronal mass ejections coming out. And that is like, in addition to the solar wind that's always pressuring these magnetic fields, it's like adding on some extra energy that's coming that way, which makes the auroras across the whole solar system.
Perfect.
Every planet that has auroras, they will bright even more brightly.
And now I have a question for you.
Yeah.
How do we know in NOAA that things are happening on the sun?
That's a really good question. Thank you so much. So as you might recall, when I started talking about NOAA, the National Oceanic and Atmospheric Administration, I said how we observe the Earth to understand all its systems, how they look right now, how they've looked in the past, so that we can predict how they're going to look in the future. Well, one of those systems, we're talking about it, the magnetosphere, right? This Earth's protecting magnetic field, which is important for us, right? And we're going to dive into it a little bit more. This protective field keeps us safe from all these particles that are coming from space. We have the auroras happening too.
And when something happens on the sun, NOAA is the agency.
And NOAA is the agency that's looking at the sun 24/7, non-stop.
Very good. Okay, that was our plug. So now we're going to move to our next planet here. Okay, so we have these giants. Now, what is next?
So when, as we move, right, we've gone through all the rocky planets. We started talking about Jupiter and Saturn. Now, here's two more giant planets that are mostly a mystery to us, believe it or not. We've only had two different missions. NASA has sent two missions, the Voyager missions. So the Voyager 2 spaceship made a stop by at Uranus and later at Neptune, and that's the only close-up data that we have. So this probe was launched in the 70s. It reached Uranus in the mid 80s and Neptune in the late 80s. So since then, we haven't had another man-made object near these two planets, right? We have had missions to Saturn and to Jupiter and to other planets, but not these guys, unfortunately.
Okay.
So there's a lot of mystery still enveloping these planets. They're not as large. They're giants. They're gas giants. They're not as large as the other gas giants, right? And because there's so much out there, they've actually been able to accumulate the same composition, hydrogen and helium, but a little more water and a little more ammonia. It's still a very small component of it. The majority is helium and hydrogen. Hydrogen is still the major gas. But those other components that are in it make us refer to these planets as the icy giants, right? Because we know that there's more icy components in them. There's more freezing happening. Methane is freezing. Methane is forming clouds and raining at different places. Remember, in Jupiter, it was ammonia. Here, and in Venus, it was sulfuric acid, right? So yeah, because here it gets cold enough where methane will form clouds and it will precipitate.
Yeah, but that's very interesting that we went from the giants, now we have the ice giants. But if you don't know about it a little bit more in depth, you will believe they are made of ice, like water, but they are not. Actually, they are called ice giants because they are so far away and they're so cold.
Thank you. Yeah, and they're so cold on the surface, right? But in the interior, the same processes that are happening at Jupiter and Saturn are happening in Uranus and Neptune. There is gravitational accretion happening inside. There is a metallic hydrogen core in there, an area that goes from liquid to hydrogen. Beyond that, inside, there's probably an icy, in Neptune and Jupiter, Neptune and Uranus, there's probably a more rocky and icy core in the middle of it. But again, we know very, very little about these planets to, really be certain about that.
Let's take a look at this picture that we got from Uranus.
Yeah.
So what can you tell me about this, Rafa?
Yeah, so, you can see here a couple of things, right? So one is this beautiful ring that's around Uranus, right? So we know Uranus, like all the other giant planets, has an accretion ring around it, just like Saturn's rings, right? It's just that the other planet ones are much more fainter. They're not as strong and not as wide and visible as Saturn's. But you know what? Over time, Saturn's rings are probably also going to start looking a little bit weaker, unless there's like another event where maybe one of its satellites, breaks up and more ice is provided to it. That ice, little by little, is not only falling into Saturn, but it's also getting darker, right? That's losing all that shine. That's what's happened to all these other ring systems. Jupiter has a ring system around it too, but it's hardly visible because of that. Now, the other very interesting feature that we can see here is that there's like some flashes on some parts of Uranus. Do you know what that might be?
I'm not completely sure. What are those?
Well, we were just talking about it. We have auroras as well. Aurora. So having an aurora on these planets also indicates what we've been indicating so far. You need a dynamo inside the planet to generate this magnetic field that will interact with the sun's solar winds, right? And when it interacts, you can see these things happening around it.
And every time we have been mentioning a lot the magnetosphere, and it seems to be really, really important because planets without that magnetosphere completely barren from any atmosphere.
Completely their surface completely changes, right? So yeah, it plays a big role.
Okay,
sure.
So let's move on to the last planet in our list.
So the next planet in order is Neptune. You know what? I forgot to mention something about Uranus.
What is it?
Uranus, contrary to all the other planets in the solar system, is doing something weird with its rotation.
I think I know what it is.
Yeah.
It's actually very, very tilted towards the pole, right? It's
That's
not
right.
Straight, well, almost straight like us. It's very, very tilted.
Yeah, when all planets are rotating on themselves with, kind of like a north to south axis, right? Uranus actually is tilted to its side, almost 90 degrees.
And that's why we can see it like that.
That's why we can see it like that. That's exactly right.
That's perfect.
So, what's happening here then is that Uranus, and I have some of these numbers here because I don't know them exactly by heart, but, we're talking about 84 Earth years to complete a full orbit around the sun. So that means that it's spending 20 Earth years in the winter, just pure face with like the South Pole facing the sun or facing away, right? For 20 years, then the side for 20 years, and then the other side of the planet for 20 years. So these, imagine the Earth, which doesn't have a tilted axis, just imagine spending 20 years in the summer, right? What that would mean for the Earth, right? Well, here you have this planet that spends its whole South Pole facing the sun for 20 years, while its North Pole is completely, pointing away from the sun.
That's very
And then as it orbits around, right, the other part comes into the sun's view, and that creates a lot of chaos in Uranus. The atmosphere, which is very indistinguishable, it's very hazy, and it's very hard to see any banding. Probably there's no banding because of this, because this extreme difference between it being pointing to the sun and getting, superheated. Again, we're talking about like very low temperatures way out in the solar system. But that tiny difference in temperature is enough to make different compounds like methane vaporize or, form clouds and stuff like that.
That's a very, very good point. Okay, let's move to Neptune now.
Yeah. So, back to Neptune. Thank you. Very similar to Uranus, not as cold as Uranus.
That's very interesting.
Right?
Why?
Well, just as we were saying before, just because you're closer to the sun doesn't necessarily mean that you're going to be hotter, right? Now, Uranus, don't get me wrong, Uranus and Neptune are very cold in their surface, and it's not like it's a huge difference of temperature like we saw with Venus, right? In this case, the temperatures are very similar, but it is believed that because of that tilting that Uranus has, that north, the side that's pointing away from the sun is going to get very, very cold, much colder than any part of the atmosphere in Neptune. So, again, these planets have internal energy coming out, right, from that accretion that's happening. And they also have these different characteristics for the clouds and trying to exchange the energy. But if you tilt that planet sideways, it's really acting very differently.
Yeah, that is extremely interesting. Okay, so
one last thing I want to mention about Neptune, if you notice, it also has a black spot. Let's see if we can put, there it is. So this, like Jupiter's red spot, this is an anticyclone, actually. You would think, the red spot and this spot, they're probably like big storm, low pressure. No, actually, they're high pressure zones. They have higher pressures. They're very cold, probably colder than all the surrounding areas. But because they're rotating in an anticyclonic fashion, that's indicating that it's high pressures that are happening there.
Very interesting.
Yeah. Now, this one does not last as long as the red giant hotspot in Jupiter. Jupiter's red spot, we've been observing it for at least 350 years. Imagine living in a storm that long.
No, thank you. Okay.
And what we're doing is here, that other storm here doesn't last as long because we observed it and then it went away.
Very good. Okay, so as we mentioned a couple minutes ago, we are missing one planet. So let's go to talk about this planet. Now that we have been gone through a tour of the whole solar system, we have learned a little bit more about what climate is not in different planets. Let's talk a little bit about our climate now.
Let's do it.
Okay.
How many systems do you know are on Earth?
That's a tough question. Are you going to grade me? I hope not. At least 5 or 6.
So, we all recognize, the atmosphere. The atmosphere.
Absolutely.
Is, we live in it. We breathe it every day, right? The atmosphere is also what's helping us regulate our temperature here on Earth. We're not having the same problem folks in Mercury have. Well, nobody's on Mercury. But if there were somebody in Mercury, right, they'd be like getting really hot during the day, like boiling and vaporizing, and then freezing solid at night, right? Without even moving from the same place.
Yes.
On Earth, though, thanks to this envelope, this atmospheric envelope that we have around, it's able to distribute that heat that we get along the equator and on the sunny side of the Earth, so that all of it keeps a relatively constant temperatures around, right? With differences between the equator and the poles, of course.
And that's another big difference with another planet like Venus that has a very thick and dense atmosphere that distributes heat all around the planet almost the same. And in Earth, we can enjoy different weathers in different places, different temperatures. In Venus will be everything the same all over the planet, right?
That's exactly right. Yeah, that's how strong that greenhouse effect is in Venus. And the clouds and the atmosphere is so thick, actually, that if you were to be looking at the sun on Venus, you probably just see like a lighter blob in darkness. So you wouldn't see the disk of the sun, because that's how thick the atmosphere and clouds are. So you don't really get to feel that heat, that the sun's heat, right? All you're feeling all around you all the time is all the heat that Venus's atmosphere is trapping.
And now something that we have, and I'm sure no other planet has, is an ocean.
Our hydrosphere.
Let's talk a little bit about our ocean there.
Yeah. So the hydrosphere, another one of those Earth systems, right? Now, what do you think is in the hydrosphere?
Well, everything that has to do with water, from ice all the way to clouds, I think, also.
Yeah.
Because they are also
lakes, rivers, right? Wherever there's water on Earth, with the biggest deposit of the hydrosphere being our ocean, right? And that makes us an ocean planet, folks, right? That's how important the ocean is for us.
And in this visualization, for example, we can see the ocean a little bit different. So these are actually currents on the surface of our ocean. And we are showing with the colors the temperature that those currents have. And we can see something very clear around the equator, right, Rafa?
Yeah, there's this like hot area around the equator, right? Which obviously is where the sun, because of the sun's angle, depending on the season, there's a tropical area on Earth, right? Depending on the season, the sun is going to be directly above the equatorial areas. And in places like this, you can see that along the Atlantic, you have all that heat along the equator that's being trapped in the ocean. But it doesn't just stay hot there, right? What is the ocean trying to do? The ocean is trying to make the temperatures equal across the whole globe. It's trying to move the hot water into where there's cooler water. These are convective forces, right? Happening at the surface and at depth, and moving it all around. And what's interesting here is you can see that because of the rotation of the Earth, a lot of that water is being pushed towards the west. And in the Atlantic, that hot water accumulates around the Gulf of Mexico, right? And if you could tilt it down just a little bit for me. Oh, thank you. Put there that's a little too much. Just a little bit less so that we can see, yeah, right there. So what you can see there is that heat that's coming out from the Gulf of Mexico all the way over there is then continuing its traveling northbound, right, all across the Atlantic and all the way to the other side of the Atlantic, to countries like Spain and Great Britain. As I mentioned, I'm originally from Spain. And I remember being in the waters of Galicia, which is right there in the northeast part of Spain in the September, October time. and I was swimming in the Atlantic Ocean, and I wasn't freezing, right? And folks, Galicia is about at the same latitude as like north of Boston. So, you know, it gets cold there, right? But thanks to this current that goes across the Atlantic, regulating temperatures, bringing warmth to Europe, and making Europe not be as cold as it would be without this transport of heat around.
And that's another of the very peculiar characteristics that our climate and our planet has, that no other planet has.
No other planet has.
Okay, so now we have another thing here that we have been talking about, all this ice. So let's talk about the cryosphere.
So the part of the hydrosphere is the cryosphere, right? Wherever it freezes on Earth, we have the cryosphere. And you know, the cryosphere is, you can see it almost like a living being, right? What you're seeing here is from December of 2023, where you can see the extent of ice in the North Pole. Juan Pablo here tilted the Earth towards us a little bit so that we can see North America here, and towards the north over there, what you're going to see is over time, we're in March now, we're going to go into April, and you're going to start seeing how that sea ice is reaching a minimum. It's getting smaller and smaller, shrinking, right? Yeah. And this happens every year, folks. As the northern hemisphere gets warm because of the northern hemisphere summer, June, we're in June right now, we're going into July, you can still see that shrinking happening of the ice there, right? And that's because in August, right? And now in September, we're going to reach what's called the minimum. Every year in September, the polar ice in the North Pole reaches a minimum. And as we were talking about before, NOAA is continuously not only monitoring, but also measuring how this looks like so that we can understand that record, right?
And you know where we can see that too? We actually can see that too in vegetation. So let's take a look at that.
Absolutely right. Yeah, so here, same thing. We're going to look at over time how vegetation changes on Earth. And what you'll notice is that following that same pattern, right? You have vegetation that is climbing up towards the poles when it gets warm in the summer, right? And when there's more light in the poles. But then as the winter starts coming, the opposite is going to happen. You're going to see all that chlorophyllc activity in vegetation kind of like moving south. And in the southern hemisphere, the opposite happens, right? And at the same time that we're losing chlorophyllc activity in the northern hemisphere and there's less vegetation, the southern hemisphere, which has less land, it doesn't have as much land as the northern hemisphere, but the same thing happens. The vegetation kind of like blooms down there.
And let's look at the same in the ocean.
Thank you.
Because in the ocean, there is also a lot of life.
Yeah. And actually, you know, there's sometimes when we think about like, where does the oxygen we breathe come from? We think of trees and vegetation. Well, a lot of it, around half of it is coming from the ocean. There's a lot of chlorophyllc activity happening in the ocean. And the same thing happens. The currents are pushing nutrients and organisms around. And this chlorophyllc activity, as we get closer to the summer, it gets closer to the poles. But as it gets colder and winter comes around, chlorophyllc activity ceases in the poles.
Very
right?
good. Very
you
good.
can only have chlorophyllc activity if there's sun. If you don't have sun rays, chlorophyllc activity shuts down.
Now let's talk about one more thing that we haven't been mentioned through the program. We said we were going to go in detail. What is this, Rafa?
So here's one of the other Earth systems, the magnetosphere, right? And what you're seeing here, now these lines that you're seeing painted here to the surface of the Earth, they extend out into space. So the Earth has like a magnetic envelope that extends way out into space, right? But what we're seeing here are the lines of that magnetic envelope.
Yes, and they converge at the poles, right?
And they converge at the poles, and that's where the auroras happen, right? Because if you may, the weak spot of our magnetic field are the poles. It's where the lines go in, right? So on the outside, when we say, you know, in Star Trek, when we say shields up, right? And that protects your whole ship, right?
Ship.
Well, imagine that the ship had a hole in the top and in the bottom, right? That's
Yes.
a little bit what's happening here. But because we're oriented the right way, right, all that solar wind and all those things just, our magnetic field protects us, and some of that energy comes in through the poles and creates the auroras.
And we might be able to see it tonight or tomorrow.
Hopefully, yeah.
Okay, folks. Well, we have been going through our whole solar system. We have contemplated many climates and many planets, and we have ended up with the most beautiful of all of them, of course, the Earth. And honestly, when I started this, I was giving Earth maybe not all of the credit that deserves it, because we have been seeing planet after planet, and we just have the right distance from the sun, the right temperature, the right atmosphere, the right composition, the right moon, the right magnetic field. Everything is just right in our planet.
Yeah.
So, and again, that gives us a huge appreciation of our planet, and we definitely have to take care of it.
Yeah. And you brought it up very quickly. The moon, is yet another thing that keeps our climate stable. So thanks to the moon orbiting the Earth, our tilt stays very stable. Other planets like Mars that don't have a moon as big as ours, their tilt is unstable.
Okay.
So I think we have some questions maybe around here, right?
Sure. Let's take a look at the questions.
Let's take a look at questions.
So, for example, we have James who's asking about Europa's ocean.
Yeah, so we didn't talk about the satellites of the giant planets. So a lot of those giant planets that we talked about have a lot of moons, a lot of natural satellites orbiting them, and some of those moons even have atmospheres around them,
And
right?
this is Europe, by the way.
And Europa specifically doesn't have an atmosphere per se. It's covered in a frozen cover, but we think that underneath that frozen surface, there is an ocean underneath it, right? Which, some science fiction authors have even ventured to say that there might be life there as well, right?
That's very interesting.
Yeah.
Okay, we have a very interesting question that I don't know if you know the answer to, but I'm very, very, very curious about it. Iska is asking us, do we know where the CO2 in Venus came from?
That's a really good question. So CO2, carbon dioxide on Venus, is coming from its rock cycle. So on Earth, before we had biological entities on Earth breathing CO2 out, there was some CO2, some carbon dioxide on Earth that was produced from the volcanic activity, from the different rocks colliding against each other and creating new compounds. And as they subduct, thanks to that tectonic activity, that carbon gets released again into the atmosphere, right? And that's a cycle, a rock cycle. Of course, the biological cycle makes that even more interesting, creating a carbon cycle, right? A full carbon cycle that's not just rock, but also biological. On Venus, we don't, as far as we know, we don't have a biological cycle. So it's all carbon dioxide coming from that rock cycle, from a carbon cycle based on a rock cycle, and from all that volcanic activity that we were talking about on Venus, right? Perhaps the reason that because it doesn't have tectonics, because it might be having like global resurfacing events that might release so much carbon dioxide into the atmosphere that's why we're seeing what's happening on Venus.
Very good. And maybe we have time for one more question. And I'm going to read this one from Derek, who's asking how were the high winds measured for Uranus and Neptune?
Yeah, so that again, these Uranus and Neptune are very big mysteries to us still. Unfortunately, we would like to know more. Now, what we have done is, as the Voyager 2 probe was getting close to them, it was able to take imagery showing how the planet's atmosphere is moving, right? And we are able to see how the magnetosphere, the planet's magnetic field, was moving. The magnetic field is what's fixed to the planet, right? As the planet rotates, the magnetic field rotates. Mm-hmm. The difference between the magnetic field and the atmosphere's movement is what tells us how the atmosphere winds are moving.
Very good. Okay, well, that's all we have today for everybody. Thank you for joining us. And again, hopefully we gain a much bigger appreciation of our planet. I definitely did. What about you, Rafa?
Yeah, I mean, when I think about places like Venus, where it doesn't matter where you are, on the poles, in the equator, you're gonna be in scorching hot temperatures all the time, you know, and under that great pressure. Really, the only difference you'll find in Venus is if you change the altitude you're at. But you know, no matter where you are on the surface, we can't go there. Mars, interesting to visit, but can we really live on Mars? Can we have children on Mars?
Well,
probably not, right? Our bodies need gravity when we're forming inside our mothers.
I would say we already have a home, so let's take care of it.
Let's take care of our home. Let's visit other planets. We love them and
Yes.
learn more about them. But let's make sure we take care of our home because it's the only one we have.
All right. Thank you so much, Rafa, and thank you everybody at home.
Thank you, Juan Pablo. Thanks, folks. This was wonderful.